The names of people that I've known and worked with. So thanks for taking the time out to come and listen to the webinar. So what we're going to do is we will go ahead in the outline for the webinar is we'll talk a little bit about detectors in ICP-OES. We'll talk about how solid state or charge transfer devices handle the charge. Get just some background info on that. We'll look at the new CMOS detector that we've introduced and compare it to the previous generation that we've used. We'll look at some performance of the new detector, and we'll look at a new feature that's introduced on the new detector called qualitative full frames. So historically, detectors that have been used in ICP-OES are classically photomultiplier tubes were the first detectors used, and those have been pretty much supplanted by the charge transfer devices, either the CCD or the CID. Photomultiplier tubes were the original detectors used in ICP, used up until pretty recent. There are still a few systems available that use photomultiplier tubes. Photomultiplier tubes are very close to the ideal single-channel detector. I mean, they were used for years in ICP and other technologies. They are excellent detectors, very wide dynamic range, but also they were very linear over that dynamic range. Had an absence of read noise, so they were capable of measuring very, very few photons. And they also have very low dark current at room temperature. Wasn't necessary to chill these type detectors to get performance that was required. And they had very high gain, and that's because they had photomultiplier tubes. So one photon in would result in 1 million or 10 to the 6th or more electrons out. So you're capable of using them with very short integration times. So typical integration times on a simultaneous PMT system may be 10 seconds. On sequentials, maybe 1 or 2 seconds per element. And that was possible because of the high gain. The downside to PMTs is, well, they're expensive, very high cost per channel. And on the simultaneous, you had a limited number of channels. You could only fit so many photomultiplier tubes on a focal plane array. And if you had a lot of photomultiplier tubes, you may not be able to use the primary wavelength for a particular element, depending on what other elements you had on there. It was expensive to upgrade them in the field. So if you had a system that had 25 elements and you needed element number 26, it would be expensive or very difficult to be able to upgrade that in the field. Some systems had to be returned to the factory to have that one additional photomultiplier. They had really limited wavelength coverage. You had so many PMTs and that was it. You had a very small wavelength range around each PMT because they were dedicated to a single element. So you didn't get a lot of the spectral information that was available in the sample. And then finally, the background correction was not simultaneous. There were different ways to do that, refractor plates or what were called spectrum shifters. But the background correction measurement and the analytical measurement were not made at the same time. And so that allows a little bit more uncertainty in the corrections. Okay. Then moving after a number of years of the PMT were available, charge transfer devices came on the scene. And they're not new devices, they were invented a number of years ago. The charge coupled device invented at Bell Labs. And if I'm not mistaken, I think the inventors won the Nobel Prize for that. Then the charge injection device. The first commercial use of these detectors was in the early 1990s. Right? Charge transfer devices, what are they? Well, they're just a two-dimensional solid-state array detector consisting of some number of pixels, anywhere from about 70,000 to about... The largest detector available now is 28 by 28 millimeters. Others can be about 19 by 13 millimeters, but they're small, relatively small. They have very high quantum efficiencies, better than photomultiplier tubes over some wavelength range, but no signal multiplication. So one photon that hits the detector generates one electron or one electron hole, and the instrument does not multiply the signal after that, or the system. So you'll notice with charge transfer or solid-state detector systems, integration times tend to be longer, and that's the reason. There is no multiplication of the signal. They have very low dark current when they're cooled, and they typically cool to about minus 35 degrees C or so. At room temperature, they're far too noisy to be able to be used for ICP-OES, so they're chilled, and they're all chilled to different temperature levels, but somewhere down around minus 30 or so degrees. That's a typo. It's in the minus on there. Well, why did people go to charge transfer devices? Well, it gives you complete wavelength flexibility, so you can see the entire spectrum from the lowest possible, shortest possible wavelength to the highest that the instrument could see. So if you wanted to add an additional element or wavelength to a method, it's simply entering information into a software program. It didn't require any hardware changes. It also will have simultaneous measurement, so that the analytical line and the internal standard are measured at exactly the same time. So that gives you the highest possible precision. It helps when people are looking at things like elemental ratios. The precision is better. And for IECs, the corrections are, again, made at the exact same time. It also has simultaneous background correction. So when the analyte is measured, so is the background, and that enhances any coincident noise rejection. It's best to be simultaneous, and that's one of the advantages of using solid-state devices in most cases. Okay. And one other thing, it does simplify manufacturing. So the benefit is to the people who make these systems. All the optical systems are the same. It's not like with multiple PMT systems or simultaneous, where you may be building 10 simultaneous instruments with each one of them totally different than the other. So it does simplify the job of the manufacturer. All the optical systems are the same. Okay. There are also Echelle solid-state systems are used with the Echelle optical systems. At Leeman Labs, we've always used Echelle optical systems. We used them with PMTs. And then when we developed our solid-state system, of course, we kept the Echelle system. Echelle systems are capable of very high resolution, very good dispersion. They're very simple and very, very reliable. And sort of an example there of a schematic of the optical system on the Prodigy7, which we'll talk about in a bit, and an example of the resolution of the thallium line, which is 7 picometer resolution, almost baseline resolution of the thallium doublet. So these systems are capable of very high resolution over a relatively small package. Okay. Basic structure of a charge transfer device, and these are just schematics. These aren't meant to be interpreted as accurate engineering diagrams. These are my interpretation of the way they look. But basically, you have a substrate, which is the mechanical support of the device. It's doped silicon. What's called the epitaxy is the photoactive area, and so that will mean this area right in here. Depending on whether the device is a CCD or a CID, the material, the doping of the epitaxy is different. It's P doped for positive charge, doped for silicon, and negative for CIDs. There's an insulator that ensures the insulation between the epitaxy and the gates. And the gates are what allow the charge or the photons to pass through. And charge is stored below the gate when you apply potentials, and that's how these devices make measurements. There's a potential well that will exist in this epitaxy region, and that's how the device will handle charge. Okay. So when photons hit the epitaxy, they'll generate electron holes. In the CCD, when you apply a potential at that gate, it forces electrons to collect in the potential well. In the CID, an applied potential forces holes to collect in the potential well. Then how the charge is handled from this point on depends on whether the device is a CID or a CCD. Okay. For CCDs, the gates are partially overlapping, and the gates are overlapping, and what they do is they pass charge through by changing the potential on the gates, you can pass charge from one row of the CCD to the next. And then once it gets to the end of the device, then the charge is shifted to a serial register where it's measured 1 pixel at a time. The thing with the CCD is for one individual pixel to be read, all the pixels before it have to be read. So this is how the charge is moved. We have some charge in a potential well. We have a certain potential on the gate. We then move the potential from one gate to the next, and we can simply move the charge across to the next pixel and then to the next row, so on and so forth, up to the serial register. So if we look at a CCD device, we have all these pixels. We'll move the charge in the vertical direction, one row at a time, and then this row passes to the serial register, and then the serial register will move to the left, to the right, to the readout, and where then the intensity or the charge in that particular pixel will be read. But to be able to read any one individual pixel, we have to read all the pixels in the device that are located before it. Okay. Another feature or property of CCDs is that they're not capable of what's called random access integration, so they can't interrogate an individual pixel. They have to measure all the other pixels that are in line with that and the output. And they're also incapable of non-destructive readout. And what destructive readout means is when I determine the charge on a particular pixel, the charge is destroyed after I do the reading. I cannot monitor the charge by repeatedly reading, which would be a non-destructive readout. Okay. Another feature or property of CTDs is blooming. Any pixel holds a certain amount of charge in what's called a full well capacity. It can only hold a finite amount. On the CCD, when that amount is exceeded, it spills over into the surrounding pixels. There's no way to tell that that's happening before the measurement's made. And what can happen there is it can cause low signals or low intensity signals to be swamped by larger ones that happen to be nearby. So for an example in the photo on the right-hand side there shows blooming in the vertical direction. CCDs can handle the blooming. They use anti-blooming circuitry, and there's different ways of doing that. The circuitry can consume some of the pixel area, and that can reduce the quantum efficiency because now the surface area of the pixel is smaller. There are some hardware designs that attempt to deal with this in one way or another. You can have a segmented system where you don't have continuous pixel coverage, or you can also use linear arrays that are stacked in efforts to reduce the effect of blooming. Okay. Charge for CIDs don't have to move the charge very far. The CCD has to move the charge to some point off the chip. On a CID, each pixel contains its own charge collection and measuring circuitry. So it's possible that when you are doing an acquire or when you're integrating signal, the device can look at the amount of charge in a pixel and then put it back and continue monitoring so that the pixel does not saturate. Okay. And because each pixel has its own collection and measuring circuitry, you can do random access. So you can interrogate any pixel on the device or any group of pixels on the device independently of any other pixels. So in that case, a CID is a lot like having a system with a number of different photomultiplier tubes where they are totally independent of each other. Okay. And the way the CID handles charge, very similar. We have gates, and we can pass the charge back and forth between the two gates. Essentially, the detector, the detector is capable, to prevent saturation, the detector is capable of looking at the charge in a pixel. If it gets above a certain threshold, clear that threshold and then start measuring again. So it's not possible for blooming to occur because I can measure the charge before it gets to a saturation state. Then once the the measurement is done, the charge for all devices just gets injected into the substrate, and then the device is ready to make its next reading. Okay. Okay. So CID or CCD, Teledyne Leeman Labs, we introduced our first CT charge transfer device based ICP in about 2001. We chose to go with the CID technology, and that was called our LPAD, which was Large Programmable Array Detector. And there were really three reasons why we chose the CID technology. First was the ability to do non-destructive read and to do random access integration. As important as those is at that time, a larger format detector became available, one that was 28 by 28 millimeters. When we take all three of these things combined, that's what prompted us to go in the CID direction. Okay, and the reason the large detector is important, we can just look before we get about the large detector. Some of the requirements that we looked at, so that you have to take into account for detectors: sensitivity. You want to have good detection limits. Dynamic range. I mean, ICP has really high signals and really low signals. You also want to have the device to have a good full well capacity. It's no good if your pixels are constantly filling up, because then you got to clear them, and that slows things down. Resolution, you want to have pixels small enough to make measurements, but also have a good full well capacity and also good dynamic range. So all these things have to be taken into account. Precision, you want the device to be able to give you good precision like a photomultiplier is capable of doing. Speed, sample throughput. There's a lot of work that these detectors have to do to make measurements, and there's a lot of data overhead. You want that to be minimum. And wavelength coverage. The ICP, we can cover all the way from 165 up to 1100 nanometers. You want a device that has sufficient good quantum efficiency. So the design challenge, the reason why we went with the full, or the 28 by 28 of the CID, the larger detector, is we want to take the advantage of the Echelle, which is resolution and dispersion, and to be able to fit the entire spectrum on the device at one time. Before we manufactured CTD instruments, or solid state detection instruments, we had a photomultiplier tube based Echelle that had outstanding dispersion, and by that we mean we were able to spread the spectrum out over a really wide range, and that is the essential quality of the Echelle. Taking that great quality of the Echelle and squeezing it all down to a smaller detector was just not something that Leeman Labs was willing to do until a larger detector became available. So the ideal case is I can fit everything on with one reading, from my shortest wavelength up to my longest. Right? Other approaches, if you have a small chip with a low dispersion spectrometer, there's a lot of order overlap. It's not really very usable in that case. Or you can go with a smaller chip with better dispersion, but now the spectrometer is going to require two exposures to cover the entire spectrum. Or you can go with, there's different ways, you can go with two separate detectors of a smaller size. All those solutions weren't acceptable to us, but once the large array detector became available that we could fit everything on with one reading, is the reason that we went with the CID detector. The benefits of also the non-destructive readouts and the random access integration make the device much more flexible for ICP. Okay. So this was our approach: one reading, and we can get the entire spectrum, so that we're not going to lose wavelengths or have many wavelengths fall off the end of the chip at the high wavelength side. Okay. Okay. So that was the reason we went to CID, and that was back in about 2001. So now if we look at the next generation, right? So ICP has been using the same devices now for about 20 years. Without really any major change in capability. Right? These devices have been around. Right? The problem is scientific images that we need in ICP-OES and other types of techniques in our industry, they're special. They're not just the run-of-the-mill devices. So we need to have very good quantum efficiency from 165 up to 800 or 1100 in our case. A good dynamic range, 10 to the 8, so that we're not limited by the detector. The plasma will be the limiting dynamic range of 10 to the 6. And we want noise characteristics that are really low. We want to be able to make measurements for elements like arsenic and selenium that have very, very low intensity, but we also need to make measurements with very high intensity at the same time. We want low noise characteristics. So because of this, scientific images are low volume devices, and the market, not influenced by the mass market cost structure. We don't see the prices dropping of these devices like you do on little point and shoot cameras and cameras that are on your iPhone. The reality is that consumer digital cameras and camcorders drive imager technology in a significantly different direction than we are. So it's a major undertaking for somebody to be able to go in and develop a new detector for ICP, and that's one of the reasons you've seen the same detectors being used over the past 20 years or so. But recently, over the past few years, there's been advances in CMOS technology that have made it a very, very viable choice to use as a detector. One of the big advances has been the reduction in noise. In the past, CMOS technology, images based on CMOS technology had a lot more noise than CCDs or CIDs. CTDs having the lower noise when compared to a CID. But over the past few years, the technology has progressed so that now CMOS technology, the noise characteristics of their images are as good or better than CCD technology. So when we decided that we were going to introduce a new instrument, one of the major components of this instrument was to introduce a state-of-the-art detector based on CMOS technology. Okay. So we wanted the next generation imager, and being part of a company like Teledyne has some great advantages. There's a tremendous amount of technology in the company. We do have a company called Teledyne Scientific and Imaging, and we partnered with them to develop this new detector. So we developed with them a state-of-the-art detector based on CMOS technology, but this detector is optimized for ICP-OES, taking the knowledge that we have, knowing and providing them with what we want to do with the detector. They were able to come back and design a device which was specifically designed to be used for ICP-OES. Right. And the instrument that this is part of is the Prodigy7. See just some basic specifications: 7 picometer resolution, full wavelength coverage. You have full gas control. It's also designed to be a low flow system, run at a nominal about 12 liters a minute, but does have full gas control for other types of samples that won't lend themselves to low flow analysis. So what is CMOS? Just to give some background, CMOS stands for complementary metal oxide semiconductor. I mean, they're not new devices. They've been around. They do have a significant share of the commercial sensor market, and they appear in consumer devices. Many cell phone cameras are CMOS devices. Right? So after years of development, CMOS devices now have performance equivalent and in some cases better than CCDs. A lot of high-end cameras are now using CMOS devices. Images for astrophysics and such are also been moving towards CMOS devices. Why? One advantage of CMOS too is that it has a large number of potential sites. Approximately 90% of all the foundry or wafer foundries that make these type integrated chips and such can handle CMOS technology. Uses the same resources as any microchip, so there's very cost-efficient production. It's a very mature process, so you get a lot of very high quality, and the number of rejections that you get on a wafer like this is very low. The this is an example of a wafer that's used to make the devices. So you want the failure rate to be low. Other advantage of CMOS is it's very flexible, and that allowed us to customize certain things for ICP-OES. There's a lot of on-chip circuitry, so it provides many processing functions. One big difference between the CMOS device and the LPAD is the CMOS device has a preamp per pixel, whereas the LPAD has a preamp per row. So there's a lot more processing technology capability on the device, so it's much faster, and we'll see some evidence of that in a bit. And like the CID, pixels can be read individually, so it has the same capability for non-destructive reads and random access integrations. Okay. So also, why CMOS? So the device can be scanned in different ways. So there's different ways to do readouts. So we use the device to do analysis, determine concentrations in samples. We can collect full frame images, which is basically a snapshot of the entire wavelength spectrum from 165 up to 1100. And a newer feature, which is called quantitative full frames, which will allow us to use a full frame, to take a full frame, and also to determine concentrations of elements in a sample based on that full frame. So Prodigy7 is the first ICP to use CMOS-based detector technology right now, and by all accounts, CMOS is going to be the detector technology for the future. There is a tremendous amount of development, and as time goes on, the quality and the capability of these devices is only going to improve. Okay, so here's the detector. It's designed, again, it's exclusive for the Prodigy7 CMOS technology. The size, it's about 28 by 28 millimeters, so it's the same size as the LPAD. That was one of the important design criteria that we wanted the same size so we could still maintain one reading to get the entire spectrum. It has a lot more pixels than the LPAD did, approximately 3.4 million pixels, or 1840 by 1840 pixels. And again, there's a preamp per pixel, and that really enhances the speed of the device, which we'll see that in a bit. And determined with the Teledyne scientific and imaging people, knowing what we wanted, what the dynamic range was, what the size of the detector and the resolution and everything, we determined that the optimum size for our device in our instrument was 15 micron pixel size. And we'll see the comparison with the LPAD pixel size in a bit. Okay. Other features, the detector has 40 times faster readout than the LPAD or other CID detectors, and we find that improves linearity and sample throughput, and we'll show some data on that. So it's faster analysis time. It can read up to 256 wavelengths in a single method. The maximum on the LPAD was 128, but you can, and I'll show you a plot in a few minutes. The device slows down tremendously as you add wavelengths to the method. And it also uses USB communication rather than the Ethernet that we used on the LPAD. So the data transfer rate down to the ICP, or to the PC more correctly, is 480 megabits per second. So it's a much faster device. And again, as time goes on, electronics get faster and faster, and this device is showing that also. Okay. It's a basic comparison between the LPAD and the CMOS device, and along with other available CIDs. So 28 by 28, same size as the Prodigy, almost 3.5 times as many pixels. You can see the pixel size. These two devices are identical. The only difference is the size. All the parameters are the same. Full well capacity is how much charge can be held. The Prodigy with 27 micron pixel size can hold up to 400,000. Prodigy 7, it's a smaller pixel size, so it holds an absolute number that's less, but the area is the electrons per unit area in the device is actually higher. So it has actually a higher full well read capacity. So it gives us a little bit better dynamic range. A big difference between the CMOS and the CID is the read noise. The read noise on the Prodigy or on the CID is 300 electrons per read without any non-destructive reads. And we'll look at some data in a bit. The Prodigy7 with the CMOS detector, for a single read is 30 electrons read noise. So it's a factor of 10 better right off the bat. But because we do a lot more non-destructive reads, we'll see that the overall read noise is much better. The output of the data read speed for the CMOS device is 2 megahertz, and the Prodigy or the LPAD and CID are 0.05. So it's 40 times. The data readout speed is 40 times faster. Okay. A comparison of what the pixels look like, and these are somewhat drawn to scale as best I could. You can see on the LPAD, here are the electrodes and some of the sensing devices on here. And you can see on the CMOS device, all the electronics are located up in the corner behind this green rectangle there. There is devices there, but it's sort of intellectual property when I'm not allowed to show it to you. It's sort of secret. You see that the row and column electrodes, you can see most of the pixel area is unencumbered by other things. So that's one of the reasons we get better full well capacity. We're not taking up some of the area with hardware and electronics and that kind of stuff. So 15 microns, about half, and that's what we sort of calculated out what the best compromise was. Okay. So before we talk about how the CMOS detector works, we'll just sort of very quickly review how the LPAD worked. Okay. So when you ran a sample on the LPAD, the first thing it did was it took a 2-second pre-exposure, and what it wanted to do is it wanted to look at all the wavelengths that you had in your method and figure out how intense they were so that it would know how often it would have to come back to do the non-destructive reads to keep that wavelength from saturating, right? So it determines how often it wants to monitor the subarray to prevent saturation. And also to take as few reads as possible. The device, because of its speed, wants to limit how many readings it has to take. And this was a way to sort wavelengths into sort of classes, really bright, not so bright, and really dim. And that's sort of, so what we would do is monitor the intensity in these pixels here. Do 2-second read, and we have lines that are really bright, and then we would know that, so we would sort them, so we know a line like this green one, very intense, goes up the threshold very quickly. I'm going to have to monitor that line a lot to prevent it from saturating. A line, so this could be a line like calcium. Say this other one's a line like iron. It's not very weak, but it's not a very bright line. So maybe I don't have to watch it as often. I can clear it, just monitor it at a smaller frequency. And then some elements, say like arsenic or selenium, they're never going to go to saturation. I'm really not going to have to bother measuring them at all. So before every sample, in fact, every replicate of every sample is a 2-second pre-exposure required to prevent saturation. At the end of so the advantage here though is that all elements would get the same integration time. The device did not have to sort wavelengths and use different integration times, long integration times for weak lines, short integration times, and do a number of different integrations per integration or per replicate. This device, the LPAD with this CID device, was truly simultaneous. Every element got the same integration time. The question is how many times would that be cleared? Very similar to channel cards and capacitors on photomultiplier tubes. At the end of the integration time, there would always be this leftover charge, and that had to be dealt with. And depending on the level of that charge, so at the end, that was called the cleanup read. So at the end of that integration, a cleanup read's done. We've got to account for those electrons that are left over, or that charge that's left over in there. Depending on the level, what the intensity or what that charge was, a certain number of non-destructive reads would be done, and it would be something in this group. So it's either 256, 128 or so. And that's done to reduce the noise. If you do just do one read, you're going to get a read noise of 300 electrons. If you do some number of non-destructive reads, you can reduce the read noise. And the read noise is reduced by the square root of the number of reads. So if you do 128 NDROs, you can get that 300 electrons down to about 26 electrons or so. Okay. The slow speed of this, one thing it does is it affects linearity, and we'll see some data on that in a minute. And also sample throughput. It takes longer to do this and transfer the data. What you really want to do, it's desirable to go as fast as you can possibly go, and you'd like to be consistent. So you want to do the same number of non-destructive reads rather than have those numbers change depending on the sample and depending on whatever's left over, right? So how the CMOS detector works, okay? Now we could have operated the CMOS just like the LPAD, but there's really no reason for us to do that, right? It has random access, it has non-destructive read, okay? The LPAD with the 2 seconds pre-read to sort everything, does it because it's relatively slow and wants to operate in a way that makes the minimum number of reads it possibly can. We're operating the CMOS the way we are because it's a very fast device, okay? And it's simpler. That's one advantage of the CMOS device. So how does that work? So first, it's not necessary to sort the subarrays by intensity. It's just not required. So right off the bat, that saves 2 seconds or so on each integration on every sample that gets run. So there's no pre-exposure, right? So what we do is we're going to run the CMOS device as fast as possible. And the reason we want to do that, the more reads, the less read noise. Square root of the number of reads is how you reduce the read noise, right? But we still monitor pixels to see if they're above threshold, of course. There's still a finite full well capacity, and we do monitor that, okay? But one difference is the LPAD only monitored the pixels in what is called the region of interest. The CMOS monitors every single pixel in the subarray. So the LPAD only monitored these 3 pixels, it's showing 4, but these 3 pixels in the middle, where the CMOS monitors every single pixel individually. And that gives us we can get a better idea of what the spatial intensities are. And also, it means on every sample, we get a nice looking scan so that things that are outside the region of interest don't necessarily saturate because we're not paying attention to them. Right. So we look at, so you can see, and this is a 3 by 27, so there's about 135 or so pixels that it's monitoring, okay? So what we do is we take a reading of every pixel in every subarray every 0.025 seconds or every 25 milliseconds. Okay? So if we integrate for 60 seconds, there's going to be 2,400 readings of each subarray and whatever number of subarrays. Okay? Then what we do, okay, is, so this shows for a 1 second integration, we're going to take basically 40 separate readings, and we construct this calibration curve. So we begin the reading, every 0.025 seconds, we collect an intensity, we go to the next 0.025, and we generate this essentially calibration curve, and then we determine a slope by linear regression. And that gives us a much more accurate way of determining what the intensity is. On a perfect device, and mathematically, we could go ahead and just measure intensities, but in a real device like this, it's actually we get better precision if we use a linear function or linear regression to determine what the intensity is. So basically, we have all these calibration curves, and we determine what the intensity is. The slope data, what we call the slope data, gets passed to the DC, And then there is a very special DLL written for us by Teledyne Scientific and Imaging that can handle all this data that's coming down over the USB. It's a very, very fast DLL, capable of incredible things. How much data? So if we do 2,400 images in 60 seconds, we'll get 2,400. Subarray is roughly about 5 by 27, maximum 256. So that means there's going to be 83 million data points coming down over that USB. One other difference between the CMOS and the LPAD is the CMOS uses floating point math as opposed to the LPAD, which is integer. And again, that's another manifestation of the speed of the CMOS device. Okay. So performance. So we've got this device. So let's see what some of its capability is. So things we'll look at are read noise, some data on linear range, some data readout, long-term stability, and then some detection limits. Okay. So this is a table of sort of read noise comparison. So like we said before, so we look down here, if you do one NDRO, the LPAD or the CID has a read noise of about 300. One NDRO on the CMOS device is roughly 30. So we'll say 30. Then as you go to more and more non-destructive reads, you can see you can get the noise goes down quite a bit. But if you look at the CMOS device, because of the great number of reads, and so it's 30 with one read, and then if we just do a 15-second integration, that's going to be 600 NDROs. That's going to take that 30 or so electron read noise and reduce it down to right around 1. If you go to a 30-second integration, which is fairly common, you have a read noise of less than 1 electron. If you plot them out together, you can see that the read noise of the CMOS device is just superior to what's on the LPAD and what's on CIDs. This data actually goes out to 2,400, but then you really can't see the effect on the LPAD. So the device is much quieter, and that's going to help when we want to do things like elemental ratios. When people do research and they want to have very high precision on elemental ratios, having smaller read noise is a definite advantage in a situation like that. So that was one other goal on the design of the device. And one of the reasons we did choose CMOS was the read noise was expected to be much lower. And again, that's in the past that was not the case. CMOS devices were noisy, but as manufacturing and research has gone on, they've quieted the device down tremendously. And it's followed the same path that CCDs and CIDs did. When they first were used, they were actually quite noisy also. So the devices get better with time. What's good about the CMOS is it's really in its infancy, so there's still a lot of improvements that can be made down the line. Okay. Linear ranges. This was data generated for an application known for 200.7. We have to determine the linear range of the various elements that are being done. And again, this is the speed of the detector is faster, so we can improve the linear range. And if you compare what was done on the Prodigy and compare to the Prodigy7, you can see the linear range is improved by a factor of 20 for some elements and by 6. So the device is faster, so it is giving us better linear ranges, and we're quite pleased with that. That was another hoped for result there. Another comparison is data transfer time. So in this plot, what we did is we created a method of some number of wavelengths, and you can see the number of wavelengths on the x-axis here. And all the wavelengths that were in the method were at 100 ppm. So we wanted to make the detector have to do a lot of work and a lot of clearing of subarrays and that. So if we look at the LPAD, if we put 10 wavelengths in there at 100 ppm, the data readout speed, and we've taken out the integration time. Both instruments, when we did one on the Prodigy, one on the Prodigy7, we used the same integration time. We did 5-second integration, 3 replicates, so 15 seconds of integration time was taken out. So to get just the net data transfer time. So you can see it took 10 elements, 10 wavelengths at 100 BPM. It took almost 30 seconds for that data to transfer down to the PC. Again, it's over Ethernet. It's a much slower communication. Plus the data readout speed of the LPAD is much slower than on the CMOS, which is reading out at 2 megahertz. So you can see as you go to higher and higher wavelengths, so when you get to 155 wavelengths, which is not very common, but you can just see as we go to more and more elements, the device slows down tremendously, where it's taken almost 2 minutes just to transfer down the data. Where on the CMOS device, 155 wavelengths takes 8 seconds of data transfer. So more realistic is 45 elements is a lot of elements to do. So from 10 to 40, even up to 80, there's virtually no change. So this will give you much better sample throughput when you have high number of elements in the method, and a lot of those elements at really high concentration. So this was an interesting plot, and we're quite pleased with the speed of the data output on the system. Okay. Overall stability. This measures stability of the entire system, not just as a detector, but we also want to make sure that the detector can read consistently over a period of time. This was a sample that was run every 4 ppm, every 15 minutes over 12 hours without any updates or alignments or anything. And we see that and we took all the data, averaged it out, and you can see the RSD over the entire run was less than 2% for all the elements. So we're happy that we're getting good stability, equivalent stability that we saw on the LPAD. So some data. And then just some comparison detection limits. Again, just to call out just a few detection limits, and the ones that tend to be important that people want good detection limits on. Just also to point out that the Prodigy7 detection limits we're running a low flow torch at 12 liters a minute. 12 liter a minute is not, you don't get the best detection limits with low flow, but we have fairly just slightly better detection limits than we're getting on the Prodigy, which is running at regular flow. So our overall detection limits are in good shape with this device. Okay. All right. So finally, quantitative full frames. All right. So back in the day, so before people introduced charge transfer devices, I mean, there were just incredible claims made for these things. Incredible claims made before. In fact, the first time I had ever seen a charge transfer device, and like everybody, I had worked for different companies and sort of wandered down into engineering, and there was some optical system on a table that they were assembling, and I asked one of the engineers, "What's that?" And they said, "It's an Echelle system." And at that time, the company I was with didn't make Echelle systems. I said, why are we looking at Echelle systems? They said, "Well, we're going to be using one of these two-dimensional detectors." Well, why do we want to do that? And so I said, well, with one reading, we're going to be able to get all the elements, all the wavelengths, be able to real-time monitor argon lines, nitrogen lines for diagnostic purposes. And these detectors they would also be really small. You'd have an optical system that would really be, just, less than 6 inches. It would be tiny. So that was back in like the late 1980s. And these devices haven't lived up to those claims yet. Certainly not be able to get one reading, to be able to get all the elements and get all that information. And the reason for that is it's difficult to collect all the information on a full frame image because of the dynamic range. Some lines are really bright, some lines are really weak. It's hard to do that with the technology that's available. It's not impossible, but it's hard to do. You'd have to take multiple readings, and do all sorts of manipulations because intensities, when you take a full frame on the LPAD or the CID system, it doesn't operate the same way. It doesn't do random access integration and non-destructive reads. It acts more like camera film. So if you expose it for so long, things are going to saturate. And once something saturates, you've lost information and you can't get concentration data from that. One of the benefits of the CMOS device is that it is fast enough and that we can read it in such ways that it's possible to get concentration information from all the elements in a sample that are very, very, very quickly. So you can get concentrations on elements that aren't in the method. And this was one of the great promises that charge transfer devices had. So to be able to do this, what we have to do is take a full frame image, right? So the speed of this detector allows a full frame to be acquired, but still taking advantage of its full dynamic range. So we can handle really high and really low intensities without saturating. And then another difference between this and the LPAD or the CID is we can now relate the intensities from a full frame to the intensities that you would get if you did an official calibration or traditional calibration. On the LPAD, the intensities for calibration or running samples were not the same as intensities on a full frame image, and it was difficult to relate them together. Things would saturate, and so it was not easy to do, mostly because things saturated so quickly. With the CMOS device, things don't saturate as much, at all, the way we can read it. So what's a full frame? A full frame basically is a snapshot of on this instrument from 165 up to 1100. So with one reading, you can get all the elements and all the wavelengths. And on this device, short wavelengths are down below, long wavelengths are up top. So we take what we call a quantitative full frame image. And when you take a quantitative full frame image, the instrument or the detector operates in a slightly different fashion than it does when it takes just what we call a regular full frame. Right? So the steps to do this, so we take a full frame image. You can do that after every sample or at any time the operator wants to request it. So we collect the full frame. Then we go to the software and there's a function called QA. So we go over to the QA button, we click it, and it will go down through and spit out what the concentrations are of the elements that it finds at primary wavelengths, essentially. And it works fairly well. How does it do that? Okay. So what we do is we have calibration curves that exist in an external method. Okay. And then what we can do is take the intensities from that quantitative full frame and pass them to this method that's able to essentially run them like a sample through these calibration curves. Right? So we compare the intensities from the full frame to determine the calibration. It's very conceptually, it's very simple. These calibration curves can be updated. They come preloaded from the factory, but they can be, and if you want the most accurate possible data this way, you can update them. You can change the concentrations. You can treat it like any method so that you can go ahead and get more accurate, close to accurate. I mean, for the highest possible accuracy, of course, you want to do a traditional calibration, but this will allow you to generate information very quickly on the concentrations that are present. So you can add or subtract different wavelengths or different lines, change the concentrations if the samples you're running. So it's a nice feature. And this is really due to the speed and dynamic range of the CMOS device. So it's a very nice feature. So it's sort of a step towards what we always referred to in the past as what we call the Holy Grail, and that you would be able to do so much with these type of detectors. One reading, and that's all you needed. You could do all your manipulations by just taking one reading and do your calibrations, everything based on that. And we're not, the technology and in the industry is not there yet but this detector takes one step in that direction, being able to get full frame images. And there's a few other things that we sort of are going to keep under our hat for other development for this kind of stuff, but there's some pretty exciting things that that we're going to get from this detector. So just sort of to sum up, we've looked at this, this detector, the characteristics of the detector. Again, low readout noise. I mean, factor of 10 better than what we had on the LPAD. It's got greater full well capacity. We're going to be able to give you better linear ranges, right? Greater speed, better sample throughput because of the data read speed. Simultaneous measurement that we're used to having with the LPAD, so that gives us better coincident noise reduction. It's better for internal standards, and it's better for interfering element correction. All the measurements are made at exactly the same time. Every element, every wavelength gets exactly the same integration. So it's a truly simultaneous system. And we also, along with all the other benefits, we still have the random access integration, and we still have the non-destructive readout, which are really integral to the way this detector performs. And that brings us to the end. And I think right now we can, I guess we go and look at the questions. Shelley?